Have you ever wondered how something as small and ordinary as a pencil can hide one of the most fascinating manufacturing processes in the world? Most people pick up a pencil every day without realizing that each one carries centuries of discovery, complex geology, extreme temperatures, engineered precision, and meticulous craftsmanship. Stay with me until the end, because today I'm going to reveal the entire journey of a pencil, from a raw piece of mineral buried deep in the earth to the finished tool that millions of hands use in classrooms, studios, and offices across the planet.
The pencil is easily one of the most widely adopted writing tools ever created, a simple yet brilliant instrument that has become an essential part of human communication, creativity, and learning. Even though it seems like the most unremarkable object on a desk, billions of them are produced around the world every year, each one relying on a surprisingly complex combination of natural resources, scientific discovery, and precise engineering. To understand how the graphite core ends up neatly placed inside a wooden casing, we need to look back in time, beginning with the discovery of graphite itself. The material found at the center of modern pencils is commonly referred to as the lead, even though it contains absolutely no lead. This central writing component is properly called a pencil core or pencil lead, but historically it became known as lead because early Europeans mistakenly believed the dark mineral was a type of lead ore. True graphite is a naturally occurring crystalline form of carbon, one of the softest minerals known to science, and when drawn across paper, it releases tiny dark particles that create the familiar gray-black markings people associate with writing and sketching. The story of graphite as a writing material begins around 1564, when a large deposit of unusually pure graphite was discovered in Borrowdale, in northern England. This discovery was so significant that it changed writing practices forever. Locals initially used the solid graphite chunks to mark sheep, but as its usefulness became apparent, people began shaping the mineral into rods and wrapping them in string or sheep's wool to prevent them from breaking. This crude design eventually inspired the pencils we know today. Graphite deposits like the one found in England formed over millions of years through geological processes involving heat, pressure, and the metamorphism of carbon-rich materials. Such deposits are relatively rare, which makes high-purity graphite valuable and historically difficult to obtain. As demand increased, miners had to dig deeper, using progressively more advanced tools to extract the mineral safely. Today, graphite is mined both in open-pit operations and in complex underground systems where workers use drills, hammers, explosives, and heavy machinery to break apart the rock. For extraction to be economically worthwhile, the mined material must contain at least 30% graphite. Once extracted, the graphite-bearing rock is transported for primary processing, where industrial crushers grind and pulverize the material into a dry powder. This powder becomes the foundation from which pencil cores will later be formed. Although graphite had been used for centuries, the modern pencil was not invented until 1795, when French chemist Nicolas Jacques-Conté developed a method that permanently changed pencil manufacturing. Conté discovered that by mixing graphite powder with clay and water, shaping the mixture into thin rods, and firing them at high temperatures, he could create strong, consistent writing cores far superior to raw graphite pieces. This breakthrough allowed manufacturers to control the hardness and darkness of the pencil by adjusting the proportions of graphite and clay, a system still used today. Once graphite powder arrives at the pencil factory, it is combined with carefully measured quantities of clay and water in large industrial mixers. The clay determines how hard or soft the resulting core will be, while the amount of graphite influences how dark or light the pencil will write. A mixture high in clay produces a hard, light-marking pencil, while one richer in graphite results in a softer, darker stroke. These mixtures are stirred until smooth and uniform, then allowed to rest so the materials can fully integrate, producing a consistent paste. Colored pencil cores follow a similar process, but instead of graphite, they incorporate colored pigments and binding agents that give colored pencils their varied hues. After mixing, the thick paste, whether for graphite pencils or colored pencils, is moved into a powerful extrusion machine. This machine pushes the mixture through a narrow funnel-shaped die under immense pressure, often exceeding 10 tons. As the material is forced through the die, it emerges in long, thin rods that look very much like finished pencil cores, although at this stage they're still too soft to be used. Freshly extruded cores are fragile, flexible, and easily bent, so they must undergo a drying and hardening process. They're first baked in a kiln at around 120 degrees Celsius for roughly 3 hours, allowing moisture to evaporate and the cores to firm up. After this initial drying phase, graphite cores, unlike colored pencil cores, are then fired once more at extremely high temperatures approaching 1000 degrees Celsius. This intense heat transforms the mixture into a hard, brittle, fully matured writing core. Colored pencil cores do not undergo this high heat firing, as extreme temperatures would destroy their pigments and binding materials. After firing, the graphite cores are soaked in a bath of special waxes or oils. This infusion fills the tiny pores in the material, giving the core a smoother writing quality and increasing its durability. The excess wax is spun away using a centrifugal machine, leaving the cores fully prepared for the next stage, encapsulation inside wood. The wooden outer casing of a pencil is just as important as the core. Manufacturers use wood that is soft enough to cut easily, but strong enough to resist breaking during use. Cedar is considered ideal for this purpose, thanks to its smooth grain, pleasant aroma, and ability to be sharpened cleanly. The first step is preparing thin rectangular slats of cedar, typically measuring about 18 centimeters long, 7 centimeters wide, and approximately 5 millimeters thick. These slats are passed through a grooving machine that carves long, narrow channels into the wood. Each groove will eventually hold a single pencil core. Once the grooves are cut, the slats move to a station where a specially formulated adhesive is applied into each channel. This glue not only secures the core, but ensures that it stays properly aligned within the wood. A metal wheel or automated feeder then carefully places the cores into the grooves one by one with remarkable speed and precision. After all cores are placed, a second cedar slat is also grooved, applied over the top, creating a wooden sandwich with graphite or colored cores neatly enclosed between the two layers. These sandwiches are loaded into presses and left to dry for about an hour, allowing the adhesive to fully bond the wood layers together. Once dried, the two slats adhere so perfectly that they look like a single solid piece of wood. The sandwiches are then sent to shaping machines that cut and shape the pencils into familiar forms, such as hexagonal, round, or triangular profiles. The design may vary depending on the brand, model, and intended use. A single sandwich often yields approximately 10 fully formed pencils. After shaping, the unfinished pencils undergo a thorough inspection to ensure they are smooth and free of imperfections. Some may be gently sanded to prepare the wood surface for painting. The painting process is performed using water-based paints, which are safer for the environment and for everyday users. Large companies such as Faber-Castell immerse the pencils into coating tanks, ensuring that the entire surface receives an even, flawless layer. Multiple coats are usually applied, sometimes 2, sometimes as many as 8, depending on the desired finish and color intensity. After painting, the pencils receive protective varnish coatings that give them a glossy sheen and guard against scratches, moisture, and wear. Each pencil is then passed through an automated stamping machine that presses the manufacturer's logo, model number, and, for graphite pencils, the hardness designation, such as HB, 2B, or 4H. Some pencils also have their ends dipped in paint to give them a polished visual finish that enhances their appearance. Next, the pencils are sharpened using high-speed sanding belts that carve clean, precise tips far faster than any handheld sharpener could manage. The sharpening machines operate with astonishing accuracy, ensuring that every pencil has a consistent, refined point. Certain pencil models may also include erasers attached to one end. If so, a small metal ferrule is crimped around the eraser and firmly fixed to the pencil body. In the final stage, each pencil undergoes a last visual quality check to ensure the graphite or pigment core is centered, the paint is flawless, and the tip is properly sharpened. Approved pencils are then packaged and distributed worldwide. Altogether, this meticulous process results in the production of more than 20 billion pencils every year, serving students, professionals, artists, and creators in nearly every country on Earth. Even though the pencil is a simple object, its manufacture represents a remarkable blend of geology, chemistry, craftsmanship, and industrial engineering, a testament to human ingenuity applied to something we often take for granted.